Yeah, so good morning, everybody. So today I'll be talking about the kinetics of polypeptide collapse, where I take polyglycine as an example, as the probe. Uh, so let me just introduce what a collapse transition of a polymer is. So it's basically when a polymer is in a good solvent, where you mean the interaction between the monomer beads and the solvent beads are the same, and then you have an extended coil phase. And in a poor solvent, since the monomer interactions are much stronger than the monomer solvent interaction, you basically get a collapse phase. And when you try to model it with a coarse-grained model, I mean coarse-grained picture, then you basically tune this collapse transition via a Lennard-Jones kind of potential and a bit spring bond or something like that. And then one can basically tune the temperature to observe the collapse transition. So at high temperature, you basically get the extended phase, and at low temperature, you basically get the collapse phase. So this collapse transition is in equilibrium. It's very well studied, and there are lots of papers, innumerable papers. So both the dynamic properties of this transition and around this transition and the static properties are well studied. But what is not so much explored was how the kinetic paths, how a polymer, which was initially in a good solvent, if we put it in a poor solvent, how it collapses to a globule. So this pathway were not so much explored. Okay. So now when I talk, so what my talk is based on this understanding of the pathway, that how extended collapse polymer collapse to a globular-like structure. So now when I talk about such a kinetics, the immediate picture which comes to my mind, yeah, this is just before that, just an motivation that why we are interested to study the collapse transitions is because of the collapse transition is an intrinsic parts, not always, sometimes, to a protein folding. Like it has been said or it has been argued that an unfolded protein can fold to its native structure directly or via a collapse transition of the backbone. Okay, so this has been explored via computer simulations as well as has been identified in experiments also. Okay, so our study, our aim is to understand basically the collapse of a polypeptide, which is basically the backbone of a protein molecule. Now, as I said, when I talk about the kinetics of a phase transition or something, the immediate picture which comes to my mind is the coarsening kinetic picture of spin or particle systems. So there basically the protocol is same, that you start with usually you start with a system which is really homogeneous and at high temperature, above the critical temperature, and then you quench it below the critical temperature where you see a phase transition, either it's a phase separation or like a ferromagnetic ordering or something. And then what happens there, that the system evolves with time by formation and growth of domains of like phases, which is where I have shown here the example from an Ising model. And the main question which is asked there is that how these domain sizes or the length scale, the relevant length scale of the problem grows as a function of a time. So we are going to ask similar questions when we study the kinetics of polymer collapse. So now before I move towards the model of our system, of the polyglycine. So here is just a background that, as I said, there were not so much studies on these kinetics of polymer collapse, even on the coarse-grained homopolymer models. But long back in 1985, Jain already proposed a phenomenological model for the collapse, for the kinetics of collapse. So where he proposed that this collapse occurs globally, so via the formation of an intermediate structure, which is sausage in shape, and then via minimization of the surface energy, you basically see a spherical globular structure. But there were few studies following this phenomenological picture, but most of those simulation studies basically showed that this Jain picture is not valid. Okay, rather they saw something which can be described by the other phenomenological picture, which came up much later in 2000, which is known as the Pearl-Nextlex picture. And there what happens basically, that when you start with an extended polymer, you initially see formation of local nascent clusters or local ordering, and then these locally ordered clusters withdraws monomers from the chain, and then they coarsen with each other to form bigger cluster, and eventually they form a single cluster, which then minimizes surface energy to form a perfectly spherical globular structure. Okay, so before we took up the study of polypeptide or biological polymers, so what we did in our previous works, we explored the same for a coarse-grained homopolymer model. So where the polymer is basically, one can say, as a non-biological polymer, so where you have all the detailed information missing. So there what we explored the scaling of the collapse time as a function of the polymer chain length, so which shows this kind of scaling with an exponent, or say with a dynamic critical exponent which is close to 2, which one can compare with the corresponding equilibrium scaling of the relaxation time with an exponent z equals to 2, which is known by the Rouse dynamics. Okay, and the most important thing which we observed, that we also observed the pearl necklace light kind of picture, and we also quantified the cluster size, how the average cluster size or the pearl size grows as a function of time, and then via finite size scaling analysis and some other techniques, with what we observed that the growth basically is linear in time, which one can compare with Oswald ripening kind of picture. Okay, so now in this project what we wanted to do, we wanted to move from a coarse-grained picture of the polymer to a real polymer, where basically we wanted to do a biopolymer, and as also motivated by the folding of protein, we took a polypeptide, and for that case, and for the matter of fact that we took the simplest polypeptide which one can think about is the polyglycine. So the monomeric or the residue of this polypeptide is very simple, which looks like this. And now we wanted to do a simulation of this, so for which, of course, you need to do an all-atom molecular dynamics simulations, where you consider each and every detail of the atoms, consider Coulombic interactions, and most importantly, hydrogen bonds, which are, of course, missing in the coarse-grained picture. And to do the same, what we did, we use this force field charm and use a package Gromax, okay, and apply the Nuse-Huber thermostats. And then what we know from the equilibrium studies of this polypeptide, that this polyglycine shows a collapse transition in water at a temperature which is close to 300 Kelvin or something. So what we did, we prepare our our polyglycine at a high temperature, but that means at a temperature which is higher than 300 in water, and then what we did, we quenched the temperature to below the 300 degree Kelvin, basically to 290 Kelvin, and then we looked at how the time, looked at the time evolution, how the polypeptide chain collapses to its globular structure. Okay. Yeah, so the first thing which one generally looks in this kind of kinetic studies is just to look at the structures or the time evolution of the structures. So those are being shown here as a function of time. So at around 20 nanoseconds, you more or less see the collapse phase or something. But unlike the homopolymer case, where this pearl necklace kind of picture was easy to identify, here since it has all these atoms and all these details, so it was really difficult to identify, but still one can see this kind of local structure formation, which becomes more apparent when one looks at the corresponding contact maps, which is a very popular way to look at the structures in the protein community. So by residue map, what I mean is basically you take up take up a monomer and calculates the distance of this monomer with other monomers, and then see if the distance is within certain distance, which in this case is the 2.5 nanometer, then you say that there is a contact between this monomer and that monomer. And that is what we plot. So this is basically the residue index, the index of the residue or the monomer of your chain along both the axes, and then you see if there is a contact, then you basically see a bright spot here. And you always see this spot, this diagonal spot, that because of the self-contact. So now if you look at these residue maps with increasing time, you can see that there are this kind of local ordering like this, which basically goes as a function of as you increase the time. So that basically signifies or again identifies the pearl necklace picture or the growing cluster size or something. And finally, you end up getting a one cluster, so where you more or less see a diffuse structure in the contact map. So by this we confirm that indeed in this kind of biological polymers, or more importantly where there are hydrogen bonds and several other minute details, that one can see the pearl necklace kind of picture. So then the next question, the next thing we immediately looked at, that since here the hydrogen bonds are really important, so we wanted to look at the dynamics of the hydrogen bonds during this collapse. So now we have to think that we are doing our simulations in water. So there are two kinds of hydrogen bonds. One is the hydrogen bonds between the polymer or the polypeptide and the water, and the hydrogen bonds which is interchain between the oxygen and the oxygen atoms of the polypeptide chain itself. So the upper one is basically the polypeptide hydrogen bonds, and the lower one is basically the polypeptide and water hydrogen bonds. And it's pretty clear that as time progresses, this kind of hydrogen bond, the hydrogen bond with the water will decrease with time, and the other one will increase in time. But the most important feature which one can notice from this one, that when you see the plot for different chain lengths, one can see that the dynamics is independent of the length of the chain, more or less, apart from the very few the smaller ones where you even do not see a collapse properly. Okay. So that's why, I mean, so this gives an information that the hydrogen bond formation or hydrogen bond breaking is independent of the chain length or something. So that means to identify the collapse time, this is not a very good candidate. So that's why what we did, as usual, what we did in the homopolymer case or the coarse-grained homopolymer case, that we again looked at the overall extension or basically the radius of gyration of the polypeptide chain as a function of time. And here in this case, that for the different chain lengths, it shows although weak, but certain dependency. And from the decay of this radius of gyration as a function of time, which one can also fit with this kind of stretched exponential distribution, one can extract the collapse time. And that is what we plotted as a function of n on a log-log scale. And this shows more or less a very weak dependence with a dynamic critical exponent of 0.5, which is much, much smaller than the corresponding exponent which one observes in the coarse-grained models. So this, I don't know, I mean, we made a strong statement that this one can correlate with the fast folding of the protein, that since the formation of hydrogen bonds are very instant and are independent of n, that this leads to the very weak dependence of the overall collapse time, which eventually may fasten the overall folding of the protein. And the last thing which we wanted to do is to now identify the relevant length scale or the average pulse size or cluster size, and to find out whether the corresponding scaling law is a function of time. But in this case, in the homopolymer case, what we did, the identifying these clusters were much easy, so we directly calculated the average cluster size or the pulse size. But in this case, it was the trick which we applied in the coarse-grained model was not applicable here. So instead of that, what we did, we plotted the probability or the contact probability function. That means the probability of two monomers which are placed along and at a distance along the contour of the chain, how it whether they are in contact or not. So that is what we plotted here, and this basically shows that as these are the contact probabilities for different times, and you see as the time increases, they are decaying at a later and later at a larger and larger distance. So that basically gives us the length scale of our problem. And by calculating the corresponding local slopes and all, we basically extracted the average cluster size, which we have plotted here. And in this case, also, if you do some kind of scaling analysis, you indeed get the confirmation that the cluster growth is still linear with time. Okay, so which is in accordance with the homopolymer model case, the coarse-grained model also. So finally, to conclude, I would like to say that we observe again the Pearl necklace-like ordering, which drives the polypeptide collapse, and we obtain the scaling of the collapse time, which is extremely fast in the polypeptide case, and the growth of the Pearl-like clusters are linear in time. And in future, what we are aiming to do is basically, instead of taking a homopolymer like polyglycine, one can construct a sequence of residues of taking many of the amino acids and try to understand more about the collapse of the protein or along this direction. And thank you very much for your kind attention.